In this tutorial, we're going to derive some simple equations for orbital mechanics. Specifically, we're talking about a satellite in space orbiting Earth. But maybe it's the Earth orbiting the Sun, or even an asteroid orbiting the Moon. As long as we keep track of gravity correctly, it doesn't matter. Let's go back to our satellite orbiting Earth. Initially, the center of our satellite is some distance r0 from the center of the Earth and has initial tangential velocity v0. As always, let's start with the free body diagram. The only force acting on the satellite is the force caused by the gravity of the Earth. However, we do need to account for the distance r. Now we apply Newton's second law in both the radial, r, and tangential, theta, directions. Let's start in the radial direction. Negative mg re squared over r squared equals the mass times the acceleration in polar coordinates. We can get rid of mass and rearrange it. There we go. Let's leave the radial component here for now. If we consider the transverse direction, all we get is the theta component of acceleration in polar coordinates is equal to 0. When we rearrange, oops, forgot my 2, we get that this derivative is equal to 0, which means that this term must be a constant. Remembering that v theta equals r omega, we can say that this constant is equal to r times v theta. And since our initial velocity is only in the theta direction, we get this relationship. The radius times the tangential component of velocity is always equal to the initial radius times the initial velocity. We're going to use this to solve a lot of problems. We're also going to use it to eliminate d theta dt from this equation. So let's make some space, and after a little rearranging, this is what we end up with, which we'll solve with a variable change, specifically u equals 1 over r. Let's clean this up. There. So, if r equals 1 over u, we can take a time derivative of both sides and get a relationship between dr dt and du dt. The product rule brings theta, then omega, into the equation, and another derivative in time gets us here. We eliminate d theta dt to get an expression in terms of r and u. And finally, we have a nonlinear, second-order specific differential equation that governs the behavior of u, which remember is 1 over r, as a function of theta. Now, we know the general form of the solution to this equation. Here it is. We can use our initial conditions to find expressions for a and b. When we put it all together and transform back to r, we get a nice, neat expression for the satellite's radial position as a function of its angular position, where epsilon is just a number that falls out of the equation. It's called the orbit's eccentricity. These two equations are the really important ones. Let's box them and get rid of all this over here for now. The eccentricity is a number, but it's not just a number. Its value tells us something fundamental about the satellite's orbit. If its value is 0, we have a circular orbit. From the equation for eccentricity, we find that the only way to have a satellite with a circular orbit is for its initial velocity to equal the square root of g re squared over r0. Any eccentricity value between 0 and 1 will give our satellite an elliptic orbit. In this case, the maximum distance from the Earth is given as follows and occurs when theta is 180 degrees. When the eccentricity is exactly 1, we have a parabolic orbit, and v0 must equal the square root of 2g re squared over r0. This is the escape velocity, because it is the minimum velocity for which the satellite will not form a closed orbit. Finally, an eccentricity above 1 gives us a hyperbolic orbit. If we make some space, we can draw out, generally, what these orbits look like. A circular orbit is, well, a circle. That's pretty easy. But increasing our eccentricity some, but not up to 1, we get an ellipse. Notice that r0 is the minimum distance from the Earth. Thus, the ellipse is not centered at the Earth's center. However, it is completely closed, and the satellite will continue orbiting around it indefinitely. When we draw our parabolic orbit, we're not going to go all the way around, and neither does the satellite. It continues out into space on the same trajectory. Similarly, when the eccentricity is above 1, the path just gets wider and wider for higher and higher eccentricity. Let's go ahead and label each of these orbits, just so we remember them, and we can make our hyperbolic orbit go out into space. And that's it! The laser-fast version of orbital mechanics. Enjoy!